Welcome to Freeslate's webinar on high-throughput large molecules formulation. My name is John Chan. I am the Communications Manager at Freeslate. I will be your host for today's webinar. Today, you will hear a presentation on the application of automated workflows for biologics formulation characterization. We're pleased to have Dr. Stephen Lambert from Freeslate as our presenter today. We'll conclude today's webinar with a brief question and answer session at the end. Before we get started, let me invite you to submit questions during the webinar presentation using the Q&A window on the right-hand side of your screen. In the Q&A window, you can simply type in your question and press the submit button. Time permitting, we'll answer these questions at the end. For any questions that we cannot get to, they'll be answered in follow-up emails. Our speaker today is Dr. Stephen Lambert. Dr. Lambert received his Bachelor's of Chemicals and Engineering from the University of Delaware. He then moved to the West Coast and did his doctoral work at UC Berkeley. He received his PhD in chemical engineering with a focus on thermodynamics and phase equilibria of polymer solutions. He then worked at Applied Biosystems in the area of assay development and automation for multiplex DNA sequencing and genotyping products. He's currently a senior staff scientist at Freeslate, where he works on applications for large molecules formulation development.
Thank you, John, for that introduction. Today, I'd like to talk to you about our biologics formulation workflow and developments we've made with that system for doing vial imaging. So here's a brief agenda for today's webinar. First, I'm going to briefly go over some common workflows used for biologics formulation development. Hopefully, these workflows will resonate with the types of things you do in your lab. I'll go over briefly the automated system we have developed for executing these types of experiments. And then in detail, I'm going to go over a new component of that system, which is our vial imaging station. And when we go over the vial imaging station, I'll talk about the hardware, the software controlling it, and as well as show some applications for particle counting, color matching, and turbidity. So in terms of the workflows on this system, there's really two types of workflows that this system will support. And what this screen here is showing is kind of a graphical representation of one of those workflows. First is a formulation screening example. The second is a formulation robustness and stability workflow. For this formulation screening example, this is usually what you do early on in formulation development for a new large molecule, where you're really starting off wanting to examine a large array of potential formulation compositions in order to build confidence towards recommended formulation or formulation space. So in this type of formulation screening example, what you want to end up with is what's graphically represented in the bottom left of the screen, which is a large array, approximately, in this case it's represented by a 96-well plate, of different formulations that you want to test in terms of for stability and aggregation, propensity to aggregate. This type of formulation array usually tries to encompass a large number of potential formulation variables, which include buffer type, pH, pH ranges, buffer concentration, the presence or absence of excipients, and you're also trying to do this with a minimum amount of material, because at this stage you generally don't have a large amount of material to work with. So these types of workflows are usually done as a kind of a plate-based screen with reduced volumes, and so they tend to involve plate-based analytics such as plate-based dynamic light scattering experiment, UV vis measurements, and also size exclusion chromatography. So the goal of these is usually to go from, as I mentioned, a large array of formulations down to a limited number that you carry forward to the next type of formulation workflow. Again, the challenges of this formulation screening type workflow is material availability, and also you tend to be doing, because of the limited amounts of material, you tend to be doing liquid compounding of formulations rather than doing large-scale, rigorous buffer exchanges into different types of buffers. And really, probably the largest challenge of these types of workflows is generating experiments that allows you to extrapolate the stability and aggregation behaviors that you see at these low concentrations to higher concentrations. So once you've done maybe a series of these types of formulation screens and your process development has worked towards creating more material, you can go to the next slide. The next type of workflow that's usually involved that you can do on our system is a formulation stability or robustness study type of workflow. And again, this type of workflow usually isn't material limited. You have much more material, so now rather than a large array of different formulations, you tend to have what we call libraries of smaller amounts, so maybe 6 to 24 different formulations. But you have larger volumes that you then daughter out into maybe replicates of these formulation libraries that you then expose to different stresses. And these tend to be longer-term stresses that can go anywhere from weeks to months. And for each one of these libraries that gets exposed to a different stress material, there's a battery of analytical daughter plates that get created from this formulation library. And so here I list kind of a lot of common analytic experiments that these formulations are tested on once they've been stressed. These include, generally analytics that try to examine both visible and non-visible particles. So these include HPLC experiments that most commonly size exclusion chromatography, ion exchange chromatography, UV vis for doing protein content, dynamic light scattering for looking at subvisible particles, and then other experiments that look at particles or aggregates such as SDS-Page, HIAC looks for visible particles, microflow imaging is also another common technique for looking for visible and subvisible particles. And so in addition, so there's really three phases to this type of formulation study example. There's a preparation phase where you're finalizing all the analytical methods that you want to look at these samples with. There's a phase where you have to assemble all the formulations. So here you are doing rigorous buffer exchange into the formulations, and then followed by compounding with excipients. Then usually a sterile filtration and a vial fill step. And then you take all these filled vials of all the various formulations you want to examine, and you assemble them into libraries. So again, here each blue box here represents basically a copy of each one of these libraries. And then when these libraries get exposed to different stresses, as I mentioned, there's usually a time zero experiment where you're looking at the as-formulated formulation as soon as it's been prepared. And then later on, then you put other copies of these libraries at different times and temperatures into different storage incubators for up to, generally 1 to 3 months, and temperatures that range from 4C up to 40C. There might be also some complementary tests that you do on these and other libraries. These include freeze-thaw tests. So you might take a library and put it through several freeze-thaw cycles. They might get some agitation tests where you shake the samples to see how that impacts aggregation propensity. And also photostability may be a type of experiment that you want to do. So then the last phase of the experiments is once you've generated all the daughter plates and collected all the analytical data, is you want to generate a report from all this data that you've collected. So there's at the end of the study, there's an analysis. You need to analyze all this data. You need to collate all this data, so you have all these daughter plates from all these different analytics, and you need to map back the well that you analyzed in that analytic daughter plate back to its original formulation library. You may need to reprocess some of this data, so like particularly HPLC. The HPLC method you may have developed for an unstressed sample may not necessarily apply to a stressed sample, say that you've had a 40C for 3 months. And so you may need to go back and adjust your analysis and processing methods in HPLC and reprocess the data so you've done all your experiments in a consistent manner. And then finally, you need to summarize all this data into a report and also potentially recommend some potential formulations to customers, and maybe also try to use this data to predict the stability of the compounds. So really what I'm going to touch on here today is our biologics formulation workflow system. And the main thing that we've added to this system is that's especially pertinent to this particular workflow is the ability to look at unopened vials and do some potential particle color and turbidity analysis of these materials while they're still in vials, both before you've done the stresses and after the stresses. So, on top of all these workflows is software to not only execute the experiments, but we have software at the start to help you design your experiments, and at the end to help you to collect all that data and visualize it and assist you in report generation. So our software, which we call Laboratory Execution Analysis, or LEA for short, really is a holistic approach. So we capture not only the execution part of doing your studies and the data acquisition, but we also assist you in the design phase to help you design your experiments, and also at the end for the reporting and data visualization that can assist you in report generation. Next slide. So the system that we've assembled for doing this, we call it our Biologics Formulation Workflow. It comes in a couple different flavors. This is kind of the full-blown flavor of the workflow. It uses two of what we call our core module systems. The right half of the core module is dedicated mostly for sample handling and sample preparation. The left-hand side is an additional core module that's been outfitted with different analytical devices and some processing tools. And the two core modules are kind of linked together in the middle by a carousel, which we use for additional plate storage and consumable storage for empty plates, vial racks, and tips. And it also serves as a pass-through between the left half and the right half for passing plates to each of the two core modules. And the whole entire system is enclosed in an enclosure, which is a low bioburden enclosure that's fitted with HEPA filters to keep particle counts down. Next slide. So here's a focus. We're looking at the right-hand side, the sample prep side, and these are pointing to all the different unit operations that we have on the system. The right arm is outfitted with two different pipetting tools. One is a 6-channel syringe pump-based dispensing system that uses disposable tips. And then also the arm is also outfitted with a positive displacement tip arm that can handle regular fluids, but also highly viscous fluids. We use it in other workflows that we have here at Freeslate for handling things such as creams and paints, etc. So it's a very highly flexible system for handling lots of different types of fluids. Other unit operations we have on the system are vortexing for mixing your samples, and as well as tip rack storage and tip waste. And then what I'm going to talk about briefly are some of the other new tools that we have on this system a little later on. So the next slide we have showing the left-hand side of the system, which we kind of consider our sample analysis part of the workflow. And here we have two analytical tools in the system. They're two plate reader type instruments. One is a molecular device, a SpectraMax, which we use for doing UV vis measurements, plate-based UV vis measurements. We also have a Wyatt Dynapro dynamic light scattering that can also do plate-based dynamic light scattering measurements. The DLS also has temperature control, so we can do temperature-controlled experiments on plates as well, such as temperature ramp experiments, which also play a big role in the formulation screening workflows that I mentioned earlier. There's also some processing tools on this system. One is a centrifuge, which allows us to do centrifugation of samples to, say, collect precipitate at the bottom of wells. And also we can do plate-based centrifugal filtration using the centrifuge. There's a plate sealer for sealing plates. So generally after you make analytical daughter plates from your samples, such as dilutions, you can move those plates to the plate sealer, seal them, put it back in the carousel, and then retrieve them to move to off-deck analytics. And then lastly, we have 3 Inheco shaker incubators, which you can use for doing plate-based stability studies on samples that you can put them in a shaking and heated environment. Next slide. So in addition to the stuff we've integrated into our core modules, we also support virtually integrated third-party analytics. And here's an example of some of those. So primarily these are HPLCs, so we support both Waters and Agilent HPLCs, and we can control these 2 instruments through integration within Power or ChemStation, and we control those through our Automation Studio software platform. This enables us to both execute the experiments on these instruments, but also take the data and save them to a database so that you can retrieve the data later. Another instrument that we also support is an Agilent 2100 bioanalyzer, and we support that through what we call our data loaders, which allows you to export files from the bioanalyzer software and then transfer those exported data files to the database for your samples. So in terms of the biologics workflow, there's 4 new elements on the core module that we've developed specifically for the biologics formulation market, because we think there's some significant unmet needs there. The first is a cooled storage bay. So on deck, in addition to just passive plate racks for holding plates, we have a cooled storage bay that's essentially like having an ice bucket on deck. It allows you to keep samples that may be sensitive, to temperature at below ambient temperatures during the course of an experiment. So these can either be source containers or your formulated samples to keep them below ambient temperatures. Another tool that we've added to that system is a multi-channel pH probe system. This has 4 pH probes that you can array in a 9 millimeter or 13 millimeter pitch, and so you can do 4 simultaneous pH measurements on samples in vials or wells. And also, one of the tips is also extendable, so that you can use this tool in a single channel mode as well for other formats that may not be compatible with the 4 or 13 millimeter pitch. Another tool we've integrated in this is a viscosity station that allows you, in combination with our PDT tool, to inject samples to a capillary viscometer, and by measuring the pressure drop across the capillary, we're able to estimate the viscosity of samples. And the viscosity range we support on here is also tailored to biologic formulations. So these tend to be formulations that are between 1 and 100 centipoise in viscosity. And we've completely automated that process, so it includes not only the injection and analysis of the sample, but washing the measurement cell as well, so for a completely unattended operation for measuring viscosity. And lastly, which is what I'm going to focus on the rest of this webinar on, is an automated visual inspection station. So this is designed to take unopened pharmaceutical-type vials and collect images of those vials to detect particles, to do color matching with known standards, and also estimate the turbidity of samples and correlate those with known standards as well. So let's move on to the visual inspection station. So first I want to briefly talk about how these are done manually today. So we really thought there was a need here to automate this process because we see a lot of companies doing this type of process manually. And this usually involves some rig where you have to hold the vial up in front of a dark or white background, and relies on people to look for particles, estimate their size, and also estimate the number of particles that they see. And the paper that we reference here kind of illustrates the fact that depending on the user, you can get a wide range of not only the estimates of the particle size that people see in vials, but also the ability to see the particles at all. So on the y-axis of the graph, you see there's a detection probability, and you can see that range goes from anywhere from 0 to 100%. So some people are very good at seeing the particles, and others are not very good at seeing the same particles. And on the y-axis, you see the estimates of the particle size that people tend to give, and that can be a wide range there too, anywhere from 50 to 200 microns. So the manual inspection has lots of drawbacks. One, it requires trained inspectors in order to reduce this variability that you see, and it can be a subjective measurement, and this lends to difficulties in validating this type of process. The type of light that's used is also going to have a big impact on what's seen, and where you put this rig set up, and the other ambient conditions around it may infect people's ability to inspect the samples. And inspectors can also be subject to fatigue. So if there's a large number of samples, so like in that the robustness and stability workflow example I showed, there's a lot of vials that they have to look at. And they're looking at them over a long-range period of time, from weeks and months apart. And so there could be some issues there in terms of consistency and the ability to see those, do that measurement consistency over a extended period of time. So we really felt that this was an obvious candidate for automation, and there was really a need there in the formulation development market for an automated visual inspection station. And the goals there are, this allows us to do a more objective and consistent measurement with using a camera. The system won't require any kind of specialized training in terms of being able to see the particles. You just need to know how to use our automation. There's the potential for unattended operation, so you can load the system up with lots of vials and let it run overnight, so you can get increased throughput compared to what you could do manually. And then at the end, there might be potential for this type of inspection to be validated. Next slide. So here I'll talk a little bit about the hardware in our automated visual inspection station. You can see the picture here on the left shows a little bit. So in the screenshot of the deck, this system was all the way at the left of the system, and the door was closed, so you couldn't really see inside of it. Here, this picture, you can see some of a couple of the internals, and you can see first our vial gripper arm, which has little fingers that can hold the vial, and it's currently extending to put the vial into the imaging station. And inside, you can see the lens of the camera, and also there's also a clamp that comes in to hold the vial in place once the vial has been placed. And what you can't see there is also an illumination system, which I'll go over shortly. So there's really three main components to the image station. The first is the camera, which acquires the vial images. The second is a rotational stage, and the rotational stage plays a key part in our ability to image particles. So we use vial rotation to basically get the fluid moving and resuspend particles in solution. And then the last part is an illumination system. So in terms of the camera, the camera uses a 2 megapixel color CCD camera. The field of view is roughly 30 millimeters by 22.5 millimeters. And what that translates to is roughly about 19 microns per pixel. So that's roughly the linear range of what you can detect. So 1 pixel represents roughly 19 microns. The camera can take multiple images of a sample, and this is, again, it will be useful for the scheme we use for doing particle detection. It can acquire images at a rate of 17 frames per second. It also has a large depth of field. We're trying to image the whole entire fluid volume of a vial, and so the depth of field here is 27 millimeters, and that's roughly the ID of a 20 milliliter serum vial. And all the images that we acquire from the camera can be stored, and we can retrieve them later for viewing or additional analysis. The rotational stage is we spin the vials in order to resuspend the samples. So the stage has a maximum RPM of 5,000. Usually we don't go up that high. We found that for 2 milliliter serum vials, we tend to use a top speed of around 2,000 RPM. And the acceleration we can do with that is about 3,500 revolutions per second squared. So we can go from 0 to 2,000 RPM in roughly 4 milliseconds. And we can also decelerate the spinning of the vial in roughly that same time period. For larger vials, we don't accelerate quite as fast. Here we can go from 0 to about 1,000 RPM in about 20 milliseconds, which we found good for resuspending particles. We can support a pretty wide range of vials in the system. Vials that are in height anywhere from 34 to 60 millimeters. This includes a stopper and metal crimp you may have on your vials. And it can handle vials anywhere from 15 millimeters in diameter up to 35 millimeters in diameter. And we recommend, so we've tested the system with Wheaton serum vials and with this volume range from 2 to 20 milliliters. And we'll show you some data using these two different types of vials. The throughput of the system, which includes the image acquisition and processing, is roughly about 2 vials every minute. So you can do, roughly, you can do 120 vials in an hour. So lastly, to image the vials, we have an illumination system. We use white LEDs to illuminate the vials from the rear. And it's also a kind of a dual mode type of illumination system where we can see the vials against either a white or a dark background. And so the details of the illumination system I show here. So on the left we show kind of the details for the white background. On the top and bottom of the background there's 2 LEDs, and the light from these 2 LEDs go into a light guide, and then attached to the surface of the light guide is a brightness enhancing film, and this is what, when you turn those LEDs on, gives you a nice white background. And so it also kind of you can illuminate your vials from behind and look at the light that passes through your samples against a nice bright white background. On the right, we kind of show what you do when you want to do a dark background. Is now that those top and bottom LEDs for the white background are turned off, and we turn on these strip lights that are kind of around the perimeter of where the brightness enhancing film was. Now with the bottom and top LEDs off that are connected to the light guide, you then get a black background, and you illuminate your samples around the perimeter. So this allows you to do the 2 illumination modes. For all the data I'm going to show you the rest of today, we found that the white background, we use primarily the white background for all the measurements. This includes, we found we get the best results in terms of for particle color and turbidity using the white background. So now I'll go into details of the particle detection. So the particle detection scheme, and as well as some examples with some standards that we've created, particle standards. So here's a brief overview of kind of the particle detection process. So you see the picture on the top kind of shows what we do. Is first you spin the vial rapidly, and then you stop the vial, and once the vial stops, the fluid inside the vial is going to keep moving for a period of time, and then it's during that period, as the motion of the fluid decays down, as the fluid in the vial stops moving, we take a series of images, and then we compare those images to look for the objects that are still moving after you stop the vial. So we resuspend the particles by accelerating the vial to a target spin rate, then stop the vial. We capture images after the vial is stopped, and then we acquire images over a brief period, generally about 500 milliseconds. We then the software algorithm then selects two of those images of those acquired, and then it subtracts those images in order to get rid of any artifacts from the vials that don't involve things moving in the fluid. So any kind of scratches on the vials or fingerprints or smudges, those will get subtracted out of the images because those are not moving once the vial is stopped. But anything that's still moving in the fluid, such as particles, will show up after you subtract the images. And I'll show you an example of that briefly. The other thing that the software algorithm can do is define a region of interest in the vial. So it can automatically detect the edges and bottom of the vial, as well as the meniscus surface. And generally, there's a bit of a delay between when you stop the vial and you start acquiring the images, because when you spin the vial, you can create a little bit of a vortex, and you want that vortex to decay back to the regular meniscus of the surface. So what the software does is automatically kind of define that region of interest to look at the fluid. The other thing that happens during the image subtraction process is there's a thresholding, and there's a parameter in the software that enables you to set that. So if you set the threshold too low, you might get a lot of noise when you subtract the images. So you want to set that threshold to a level where you actually detect particles, but you don't introduce too much noise in the subtracted images. And then from the subtracted images, we do what's called a blob analysis to look for differences between the images, and then we can do some statistics on the blobs that are found. This slide here shows some of it's basically screenshots of the software for two of the profiles that are associated with particle analysis. First is the motion profile. So this is how you can control how the vial is going to get spun. So there's key parameters for how fast you want the vial to move once you reach its top speed. There's you can set its acceleration and deceleration rates. The hold time is how long do you want, once it reaches that top speed, how long do you want it to keep spinning once you reach that top speed. There's the settling time, which is the delay between when you stop the vial and when you want to start acquiring images to allow that vortex back to decay to a nice even surface. And then once you start acquiring images, the delay between capturing images and then the total number of images that you want to acquire. And you can see there's some differences here between the 2 milliliter vials and the 20 milliliter vials. And the main difference there is actually the delay between image capture. So when you have a larger vial, things are moving around a lot faster in a large vial. So there you can, in order to detect the particles, you can have a much larger delay. The fluid motion doesn't decay as fast in a large vial, and so you can have a longer time period between acquired images. The second profile associated with particle analysis is associated with particle analysis. So these are the parameters. So this is basically how describes how the images are analyzed. So there's some parameters associated with finding the meniscus and some offsets to the vial edges. The binarization threshold is that particle detection threshold that I mentioned to help reduce noise. There's a particle size scale factor, so it's in order to convert from the size of the pixels of blobs that are found to an actual particle size. And then you can kind of restrict the range of particles that you're looking for. So so the particle area here detects the minimum particle size that you can find, and also the maximum particle size that you find. The maximum particle sizes tends to be very large, so you can see very large particles if some should show up in your vial. And then lastly, the last three are kind of some statistics, some parameters associated with how you want to aggregate the statistics on some of the blob sizes that are found. So you can bin them into different particle size bins. You can define the maximum size bin and the bin interval. Okay, next slide. So here's an example of a 2 milliliter vial. So on the left here is kind of an animated picture of two of the images that the algorithm has selected to subtract. And so I basically created an animated picture here that's kind of flipping back and forth between the two images that are acquired, and you can see the particles moving around in that vial. So the vial has stopped moving, and the fluid is still moving, and entrained in the fluid are the particles. And these are roughly 10 monodispersed 170 micron polystyrene spheres in water. This is a 2 milliliter vial with a 1 milliliter fill volume. And then on the right, you see the blob images after the two images are subtracted from one another. And so the algorithm also identifies each of the blobs, gives them a number, and we get a particle count now by counting the total number of blobs and dividing by 2. Okay, next slide. Here's an example now for a 20 milliliter vial here now where we've got smaller particles. So these are 80 micron spheres in an 8 mil fill volume of a 20 milliliter vial. They might be a little harder to see on your screen. And so on the right, I show the blob image, and you kind of see some specks from the blob image, and I've blown up a small portion of the blob image so you can see how it's labeled those blobs. Okay, next slide. So here's basically a summary of what you can do with the particle detection on the visual inspection station. So our primary application here is to screen for the presence. So that is the presence or absence of particles, of visible particulates in unopened vials. And here we define visible particulates as those that are greater than 80 microns in diameter. So that's kind of our cutoff of the system to be confident that we're seeing visible particles is those with size of 80 micron or larger. So in terms of how accurate we are in terms of particle count, what we're going for is when there's no particles in your sample, that's what the system will return. Now, you're not going to get any false positives of particles in your sample. When you have a very small particle count, say 1 to 3 particles, our goal here is to be able to detect at least one of them so that you get no false negatives in the system. And as the particle count increases, obviously the amount of variability in the system is going to go up somewhat. And so when we have, say, 4 to 9 particles, we can, at least the experiments we've done so far shows that we can get that count accurate to within plus or minus 2 particles. When you have 10 to 25 particles, that count can be accurate to within plus or minus 5 particles. One thing we should note here with the system is that we can't, at this point, differentiate between what may be bubbles, particles that are due to proteinaceous materials coming out of solution, or the presence of inorganic matter in your sample, such as rubber particles or glass particles, metal particles, etc., fibers. Where we can only detect what the blob images show us, and this is at one point where it's important that you have good motion profiles in your samples so that you're not generating a lot of bubbles in your samples. And so if you want to keep the detection of bubbles down, you have to kind of test your system and make sure that the motion profile you have for your particular type of sample doesn't generate bubbles. The blob analysis, as I mentioned, you can do statistics on those to get estimates of what we call the equivalent circular diameter of the particles that are found. And it could also do estimates of particle shape in terms of aspect ratio from minimum and max ratios of minimum and maximum ferrite diameters that you can get from the blob analysis. But I should caution here that you are looking at cylindrical vials, and so the lensing effects from the vials, particularly at the edges, can impose some imaging artifacts that can lead to some inaccuracies in some of those blobs that you get. So the statistics you get out on your particles is only as good as the blob images that you can obtain. So next slide. So here's some data showing the particle count reproducibility in the system. And so for this, we've had some particle standards prepared for us by a company called Solar Hill Engineering. We supplied the glassware, and they prepared some samples with particles in them. So they prepared 4 different types of standards for us. They prepared some certified blanks that are known to be particle-free in both, and we got some prepared in both 2 milliliter vials with 1 milliliter fills, and 20 milliliter vials with 8 milliliter fills. And then we had different particle counts and sizes. So we had 3 vials with 3 of the different size monodispersed particles, ranging from 80 to almost 300 microns. And then we had one standard where we took 1 particle each of those standards and mixed them together. So to go over the data here, the average particle counts that we get from 10 consecutive measurements of these standards is pretty close to the manual counts that we got. Certainly within the specifications that I talked about previously. The min-max, you'll notice that, especially for the particle where we have 3 particles in it, you notice that the min-max particle count we got for all 10 of those measurements, well, the min and max particle counts range from 3 to 4 in those experiments, so we never got a situation where we saw a false negative or a false positive. So like in the blank, we never saw a situation where we got a false positive in terms of the particle count. For the 20 milliliter vials, those were prepared with a lot higher numbers of particles. So the company that prepared these standards for us wasn't able to provide us with an accurate count because there were too many to count manually, except for the last standard here with 1 particle each. And you can see for 20 milliliter vials, we also get a good representation of what's in the vials. And again, the blank showed no false positives, and the vial with only 3 particles didn't show any false negatives. Okay. Next slide. This shows an example report you get from our reporting portion of the software. So this is a data browser report. So this is a report that gets generated by the system, and you can access the database through a simple web browser. So this doesn't show you all the data that the system requires, but it gives you basically a data summary for this type of experiment. So this is an example of a particle imaging or particle count report. So for each vial that you analyze, and here we've analyzed 6 vials containing a 50 mg per mil BSA solution. You get a thumbnail image of the vial before you spin it, thumbnail images of both the images before and after it was spun, and then a thumbnail image of the blob image. And then lastly, the estimated particle count from that blob image. So if you click on any of those thumbnail images, you can get a blow up, a very large. You can see a detailed image of any one of those images in detail, And in this case, I'm actually showing, I didn't clean these vials particularly well, so you can see this first vial here. It's detecting what looks sort of like a fiber in the sample. And in the blob image, you can see it's kind of, because of the aspect ratio of that fiber, it might be on the thin side. It's kind of breaking that fiber up into smaller particles. And that's part of the binarization process that I mentioned. Okay, next slide. So next I'll move on to the application for color matching. So color determination, this is done by a simple image acquisition of the vial, so it doesn't involve spinning the vial at all. And for this, color is a comparative process. So now we compare the images that you acquire for samples with images that you calibrate the system with known standards. So what this requires you to do is to take these color standards, which you can purchase from, say, Sigma Aldrich, and there's a wide variety of these color standards. We chose the BY color standard, which is kind of a yellowish-brown color standard. And this comes in a set of 7 standards. And we place those standards in with the same fill volume that you're going to use with your samples. And also that's different from the particle analysis is instead of automatically generating a region of interest, what you just now have to do is kind of define a region of interest that's a subsection of the vial image. And so the red box you can see in the screenshot below kind of shows you the region of interest that we've defined for these vials. And we found we get the best results when we pick a region of interest that's sort of centered on the vial axis, and it's away from any edges or the meniscus of the solution. And so this maximizes the path length of the light through the sample, and that's acquired by the camera. So again, here's kind of a screenshot of the calibration. So you can see there's an image of each one of what we have here are 8 standards. 7 of the standards again come from this BY set from the PharmEure color reference solution set. And here we've added our own reference standard, which we call blue. We put this in there just to show that in addition to the reference standards that you can buy, you can include your own reference standard if you wish. So for each one of these standards, when you measure your samples, you're then going to compare your actual sample to one of these standards. So the next slide, I kind of show the algorithm for doing the color matching. So first I'll talk about how the standards are handled and then how you handle samples. So for each of the standards, within the region of interest, you're going to extract a color coordinate from each one of those pixels in the standards. And the color of each pixel is described by a 3-dimensional color coordinate system. So those of you familiar with doing color measurements will recognize that we use the CIE LAB system for doing the color coordinates. Within that region of interest for the standard, you're going to get some variability around an average color coordinate. So for each standard, we define what's called a distance tolerance around the average color coordinate for the standard. So this basically creates a sphere around the average color coordinate for the standard. And so there's one of these spheres for every one of the standards that you calibrate the system with. Now, when you go to measure your sample, we then look pixel by pixel at the region of interest of your sample. And if pixel within your sample lands within this sphere, this distance tolerance sphere for one of the standards, then that pixel will get a quote-unquote vote. And if that pixel lands outside any of your standard spheres, then no vote will be recorded for that particular pixel. So for the simple example I give here, I'm looking at 2 pixels. So the pixel represented by the blue dot lands within the BY3 distance tolerance sphere. So that gets 1 vote for the BY3 standard. And then another pixel for that sample lands outside any of the distance tolerance sphere. So that that pixel does not get any kind of vote. And by accumulating all these votes for a particular sample, we can then get a quantitative assessment that we can use to match the standards, and also find out how relevant the standards that we use for the system are to our samples. So one measure, the first measure is a so-called relevance score, and this is the total number of votes for a sample for all the pixels divided by the total number of pixels. So if the majority of the pixels that you get for a sample land within any of the distance tolerance spheres for your standards, then you'll get a very high relevance score. If no pixels land within these spheres, then you're going to get a very low relevance score. That means that the sample set that you picked is not very representative of the standards that you picked aren't very representative of your samples. And then further, you can accumulate what are called match scores by seeing how many votes for a particular standard were recorded divided by the total number of votes. So what percentages of votes went to what particular standards. And then you rank those match scores and then list the standards that your sample matches best in terms of from highest match score to lowest match score. So the next slide, I show basically the reproducibility of samples. So here we've taken the samples that we use to calibrate the system now, and now we've measured them as if they were unknowns. And we can see that, and so here I list the average match score for each standard, and you can see that, say, let's just take an example for BY1. You can see that from 10 consecutive measurements, so N is the number of measurements, we can see that the average match score for the BY1 standard, so we get an average match score of 99% to BY1. So you can see that after we calibrate the system, the standards themselves very highly match you get the same standard back that you calibrated with. And this holds true for both the 2 milliliter vials and the 20 milliliter vials. Now, so the BY standards, they go from a very brownish color in BY1 all the way down to almost a color that visually is very indistinguishable from water. So you can see as you go to more colorless samples, the match scores tend to go down, which isn't unexpected because it's very hard to distinguish these materials. At least visibly, I'm unable to kind of visually distinguish, say, between BY7 and BY6, but the camera does a much better job, especially in the larger vials, of distinguishing the near colorless samples. And the larger vials do better, obviously, because there's a larger path length to pass the light through. So the next slide, I show you, again, another example report that gets generated when you measure samples. So here's, again, 6 BSA solutions in PBS. And so what you get in your report is you get a thumbnail image of each of your samples. You get a column here that shows the relevance score. So that tells you how relevant your samples are, how relevant your standards are to the samples you've just analyzed. And you can see here for BSA, the BY standards are actually a very relevant standard set to use for your samples. And then, at least here, we measure the top 2 match scores and match names. So you can see these 6 replicate samples all match very closely to the BY5 standard. Okay, lastly, I'm going to talk about turbidity. And again, turbidity is measured. It's very similar to color in that we acquire images of calibration standards in the same vials that we use for samples. So here, instead of color standards, now we're using turbidity standards, and we use turbidity standards we got from GFS Chemicals called Ampco Clear NTU standards. And just like color, you define a region of interest of the vial, again, typically near the center axis of the vial, away from the edges and the meniscus, to maximize the path length through the sample. And here, rather than color, we look at just the luminance value. So we're looking at the L value of the color coordinate, and we average the L value within the region of interest for each of the standards. And then we normalize that luminance value with what we call a blank image or a background image, which will also show in this calibration screenshot. So what this allows us to do is to basically normalize any variability in the light source that may occur over time. So as the light source ages or as it warms up, you can normalize the image you get through the vial with a background image that you acquired just before you place the vial in the imaging station. And we find that this helps to normalize over time. So a calibration you do one day is very likely to be is likely to still be valid the next day, or a week later, because you've normalized the image with the recent light that you get from the light source. And so then we correlate this normalized NTU with the NTU value provided by the standard. And here we use a second-order polynomial regression to correlate these values, and then for samples we can then back calculate a turbidity from the luminance values. So here's a summary of what we can do with turbidity. We found that using the white background, we can analyze turbidities in a range from 10 to 1,000 NTUs based on the standards that we used, and our accuracy is generally within plus or minus 5 NTU units for non-absorbing samples, so samples that don't have any color. And the reproducibility is usually within plus or minus 3 NTU units. And again, these apply to using a white background, which we found gives us the best dynamic ranges for changes observed when measuring. So now we're measuring the light that passes through the sample. So if you go back, can you go back a slide? So you can see the samples, the higher the NTU value for the sample. So the 1,000 NTU sample tends to be darker than the lower NTU value. So we're seeing the light that gets transmitted through the sample. So as the sample gets more turbid, the light gets scattered and the less light that reaches the camera. And as a result of doing it in this way, one thing I should caution you about is that sample color may have a significant impact on our ability to correlate a sample with the uncolored NTU standard. So the standards that we use here don't have any color. So if you use a colored standard, that absorbed light can kind of give you a false NTU reading. So it's something you have to think about if you want to apply the system for doing turbidity estimates of your sample, is to kind of gauge what impact color will have. Lastly, here's some data showing the reproducibility of now taking the NTU standards and measuring as if they were unknowns. And generally, we get good accuracy. The correlation gives us good accuracy of the NTU value. And good standard deviation, particularly at the higher NTU values. Those generally tend to be less than 5%. Obviously, at the low values, you get a lot more variability as we reach the limit of detection of the system. And again, the 20 milliliter vials tend to do better than the 2 milliliter vials because of the increased path length through the larger vials. So this is data that we required. Again, this is 16 repeat measurements on the same vials, and we've done the measurement. We basically did it over 30 minutes. So we repeated these measurements every 30 minutes over the course of 8 hours, and we've applied the same calibration we did at the start of the experiment to all 16 of these measurements. So it's a pretty stable system, or scheme that we've used to measure turbidity. So lastly, I'd like to summarize what we went over today. So first, I gave you an introduction to Freeslate's Biologics Formulation Workflow, showed you the unit operations we have integrated into the system, briefly discussed the types of workflows that we are targeting the system for, so formulation screening type workflows, as well as formulation robustness and stability workflows, and talk briefly about some new capabilities that we've included in the system to meet what we think are unmet needs in the formulation development area. I talked in detail about the new visual inspection station that we put on the system, and this is used for rapid screening of unopened formulation vials, to detect visible particles, to perform color matching with relevant standards, and also to provide a way of estimating turbidity through correlating luminance with known standards. And lastly, these capabilities are integrated with Freeslate's core module hardware platform and our software suite for laboratory execution analysis. So now I'll hand it back to John, and we'll take any questions that you have. Thank you for your attention.
Thank you, Dr. Lambert, for that very detailed presentation. We'll now have a brief question-and-answer session. My colleague from the product management group, David Yamani, will moderate this session. David?
Thanks, John. So due to the time, we only have time for a couple questions. So the first question that we received was, whether we've done any particle detection of proteins.
We have done some proteins in-house that we've received from some collaborators that we have. Fortunately, we're not able to show that data at this time. I guess I will say that at this point, we are looking for people to work with to look at real systems. Part of the challenge of working on the system is finding suitable standards, and we've had to kind of create our own standards. There's not a lot of particle standards in vials available out there. We've kind of had to go out and work with companies to create those. But I think one thing that we'd really like to do is to get some real samples in-house and see how well this system works on real samples.
And the second question that we have is, how does the formulation viscosity affect the ability to detect particles?
So the viscosity is going to have a big impact on the ability to detect particles. So we're relying on, by spinning the vial, of inducing fluid motion in order to suspend the particles and get the particles moving in solution. So if you have a very viscous formulation, that's going to be harder to do, since the higher viscosity formulations are going to be less resistant to fluid motion. Right now, we're targeting being able to detect particles in fluids up to about 30 centipoids. Again, another difficulty we've had here with the system is finding suitable standards for testing our ability to detect particles in viscous fluids. But generally, so that's another area where it's important that users have control over the motion profile in the system, so that they're able to change that for different types of fluids. And hopefully, when we ship the system, that we'll be able to provide guidelines in terms of representative motion profiles for different types of fluids.
Good.
Thank you, David. Because of the time constraint, we will answer remaining questions through follow-up emails. Before concluding today's webinar, I would like to invite you to visit www.freeslate.com to see our previously recorded webinars on high-throughput large molecules formulation. This concludes today's webinar. On behalf of Dr. Lambert and the Freeslate team, we thank you for your attendance. We look forward to seeing you at future webinars. Have a great day. Goodbye.